Hi, I'm Daniel Britton, and I'm really glad to be here at FTSCS. And this is a work modeling a blockchain for smart contract verification using DeepSEA, which is by myself and my PhD supervisor, Steve Reeves. And it's with building on work done by Certic on DeepSEA itself. So first of all, I'll just mention, so smart contracts are part of the blockchain, as many people are aware, and they may not sound like a safety critical system now, but perhaps in the near future they are. And also, a lot of banks consider their software to be safety critical, and many smart contract applications are banking related as well. And so this is the motivation for smart contract verification being safety critical as well. So first of all, I will just give a bit of background on DeepSEA. So this is background that is built upon in this paper. DeepSEA is a smart contract language as well as a framework that what it does is it takes the language and then it converts it into a representation in the Coq proof assistant, and it compiles this down to Ethereum virtual machine bytecode. And this is shown on this diagram here. So we start with a DeepSEA language source file, and then the DeepSEA compiler will, through stepwise refinement, will bring it down to the Ethereum virtual machine. And we use Yocho-Hirai's lem semantics for the Ethereum virtual machine. And this allows us to be sure that the properties we proved right up at the top about the smart contract hold for the actual bytecode. I will mention that that's still, in some senses, a work in progress. But yeah, as I mentioned, it targets the Ethereum blockchain as well as any other blockchain that uses the Ethereum virtual machine, which is quite a range of blockchains at this point in time. So now I'm going to introduce the context. So DeepSEA is the language and the tool. And so now there's a context for the example that I'll be talking through in these slides. So the example is a crowdfunding smart contract. And crowdfunding, so I'm sure you guys are familiar with Kickstarter or similar. The basic idea is you have a goal and a deadline, and if the deadline passes before the goal is met, then everyone who has given money gets their money back. And in traditional systems, the Kickstarter or the other company will essentially have your money in this interim period, or have some kind of hold of your money in this period. And if they were malicious, they could make away with that money. And obviously there's very good kind of legal reasons why they wouldn't do that, but in principle they could. And so the idea with a crowdfunding smart contract would be to take that centralized control away, so that the smart contract is kind of in charge, and if it's been proven correct, then there's no ways that the smart contract can make away with your money. And this is based upon the reference at the end of the slide. This is based upon Sergey's work many years ago, interestingly. And so, yeah, so the first property, this is a property based upon their paper to do with the Scilla smart contract language. So the first property that they talk about, which we also prove in for DeepSEA, is that there's the donations record, so the mapping that records how much each person has donated is backed, has sufficient funds, so that the ether in the bank account of the smart contract backs that amount. So the sum of the donations is backed by the balance. And then we want to also realize that we don't want to have a donation recorded and then suddenly forget about it. And so we want the donation record to be preserved over time. And so this is the example I'll be talking about a bit more. And then finally, we want that the backers can actually claim the donations back after the campaign fails if the goal is met. So this is the context for an example that I'll be talking through. And the context is in relation to how the model of the blockchain interacts with this example. So we wanted to provide a model for the blockchain in DeepSEA, and also, so in DeepSEA, that chain I referred to earlier, basically the refinement proof is done for individual smart contract functions. So it doesn't pull together a cohesive model of the smart contract as a whole. And so the issue here is that we need to be able to talk about the smart contract as a whole, and even more than that, about relevant aspects of the blockchain as a whole. And so the idea here was to provide a small wrapper on top of the refinement proof of individual smart contracts to bring together the smart contracts so that smart contract functions so that they are able to be reasoned about and do proofs about as a whole contract. So the main contribution of the paper is this idea called the successful calls approach. And the idea here is to try and, so big picture, we're trying to, increase the security of smart contracts, have them verified. And then zooming in right now, we want the proofs to not be too complicated, because Ethereum proofing in Coq is a difficult task. And the idea was to try and minimize the proof effort and reduce some redundant cases. So this is a diagram of, like a vaguely state machine diagram of the idea here. So we start with an arbitrary state of the blockchain. So we think about the blockchain's variables like the balances, mapping, and we just arbitrarily quantify over that to start off with. And now the green arrows represent what the blockchain can do, essentially. So it can either call these three functions, which are from the crowdfunding contract. You can either donate, get funds, or claim. And you can also model time passing and like a balance transfer that's adjacent to the contract, not directly related to the contract. And so in this model, the green lines represent the fact that, so the idea here is that instead of modeling a donate function with its arguments, and then if the arguments are wrong, then it can fail and it'll come back to this state, because when a smart contract fails, it returns to the state it was in before. What we actually do is we require, as one of the arguments to the donate function in the model, a proof that the call to donate will succeed. So we are saying, okay, when you call donate, you not only have to provide the arguments, but you also have to provide a proof that that call will succeed. And so that rules out the possibility of the donate function failing. And it's not that we are ignoring it completely. The idea is that if you imagine red arrows over here and here and here, they sort of all get just looped down into the reverse case. And so that is the idea. And now I'll move on to the implementation of that idea. So this is some Coq code as part of the model of the blockchain that we developed. And so I'll try to use the arrow here. Okay, so there's a few things to notice about this. The first is how it maps onto this previous diagram. So you can see there's donate there, and so there's a few, this is an inductive data type. So we're defining essentially the type of the arrows, more or less. So we have action, and then we have, that's the type, so donate, and then we have get funds, and this looks the same as the above, just we would swap out donate for get funds, and same for claim, we'd swap the definition. So this is kind of repeated 3 times. And then you have external balance, transfer, time passing, and revert. And so you can see how this corresponds to this diagram. And then the interesting part, the novel part, is that this proof here, so case donate proof, this is the state transformer, and then here's the donate function again. And what we have is that running essentially in the model, the high-level definition of donate gets run by the run state transformer, and it equals sum. And so we've got this as one of the required arguments for essentially calling donate in the model. And so we've got the fact that it returns sum implies that it doesn't fail. So if it failed, it would have returned none. And similarly, we have another proof, which is that there's no overflow, underflow in the transfer. So when you call a smart contract function, you're allowed to transfer money to it. And in theory, you might not have sufficient funds, or you might, in a really unlikely case, overflow the recipient's balance as well. And so that's also guarded against to guarantee for certain that the donate function succeeds. So that's our type of error. And so that's the type of all of these errors, basically. And the one other thing I wanted to point out was this is a type, right? And so we have a value of type blockchain state. The blockchain state is simply it's simply a record containing things like the balances mapping, the contract state, that kind of thing. So it's the whole blockchain state within the model. So this is a dependent type. So the action depends upon the previous state. And that's important because we need to be able to know what the previous state is so that we know that we can phrase a lemma of the type that the contract succeeds, because contract success will depend upon the previous state of its storage variables, balances, etc. So that's just important to point out as well. And I'll also just mention we have the step function. So the step function, okay, I'll just point out one more thing here. So we have R and contract state after. So this is the return value of the smart contract and the contract state after it's called. And that's used in here as part of the guarantee that this is what happens after you run the smart contract. So in the type of the action, you have the, this is the after is contract state after, and this is the return type. So you have, when you have a call, you already know the return type and the contract state after. And so all you're doing is in the step function, which is typically going to compute the next step. It just simply grabs the already proven return value and contract state after and puts it in a small wrapper for the next blockchain state. So our step function becomes little more than a wrapper, which I think is an interesting side effect. So now I'll move on to usage in a crowdfunding proof. So this is a proof that I mentioned earlier. So, sorry, this here is a snippet of DeepSEA, more or less. It's slightly altered, but to make it fit and simpler. But basically the idea is that we have a few branches over here. So we have a fail branch and a fail branch when the goal hasn't been met yet, or when the backer has already backed. So in this function, we don't allow someone to donate twice. You can only donate once. And the point here is that this branch here is the one in which we have the success. So this is what we are hoping that and this is a very simple evaluation, but does it actually target the proof towards the successful case? And so here is too big to read, I know, but this is just the whole proof of a property. So it's saying that a donation is recorded since the donation has been recorded, as long as no claims come from that person. So once you put your donation in, it stays there unless you withdraw your money after the time is over. And I'm just going to zoom in on part of this. So if you just notice the structure broadly here, we have a bullet, and a bullet, and a bullet, and two sub-bullets. And I'm just going to focus on the donate functions bullets, which are kind of the donate functions 2 bullets. And so here we have a hypothesis that is present in both branches of the sub-bullet, which is that if you get from the backers mapping the value for message senders, it equals 0. And that might ring a bell because that's what we have here. So if you get from the backers mapping for message sender, it equals 0. And so this gives an indication that the proof is focusing in on the successful call. And you can see that there's no other branches visible that are for the donate function. It's only focused on the successful call. Yeah. Okay, and now I'd like to look at another brief demonstration of what the difference is. So if you look over here, you see we have this call to like make donate no longer opaque and then unfold it. And then we call this function DeepSEA inversion, which is going to consider all the cases that the DeepSEA source file could branch into. But the idea that here is that this is what it looks like in this current proof, and this is what more or less what it looks like in an older version of this proof prior to implementing the successful calls approach. So we had a bunch of extra stuff on top, and this is just one part of where the proof got a bit messier. So the idea here is that the proof is messier. We had to do also over here is on the inversion H0 and assumption. So this is actually it's reasoning about the lemma at hand to discharge the goal, whereas in here we don't have to reason about the lemma at hand to discharge the goal. So that's one of the benefits of using the successful calls approach. It makes the proofs simpler in a variety of ways. All right, how do we time? Okay, so I'll just summarize, and I'll also just mention a couple of minor points on limitations of this approach. So first of all, the use of a dependent type for action is sometimes tricky. So a lot of the time you might think, okay, I've got a list of states and I've got a list of actions, and if I take those two lists and I apply the action every time after the state, I can get to the final state. So you can't actually have a list of actions without the corresponding states in this formalism, because the actions are dependent on the states. And so you need to have a dependent pair and wrap those two lists together, which can also cause issues with the proofs. But on balance, it's simpler, and personally, I think cooler as well. So just to recap, this is the successful calls approach, where we have only the successful calls going forward. And you can also imagine this diagram, like all of these green arrows again off each of the subsequent states. And the revert case is handled, so we don't ignore it completely. We do back over here, we have a case for revert, and so it's not completely missed out. Yeah, and as I said before, we have DeepSEA. So this is a small wrapper on top of a verified compiler down to Ethereum virtual machine bytecode. And so thank you very much. I especially would like to thank Wilhelm Scherberg at CERTIC for his conversations, and Steve Reeves as well, and also the University of Auckland and Jingson for kindly hosting me during this research. And I'll just pick up these references as well briefly. So I'd be happy to take any questions. Thank you.
Thanks so much.
Okay.
All right, so any question?
Yes, oh, sorry.
Sure. So additionally, in your successful calls approach, you're only considering the cases where a call doesn't revert, or generate an invalid state or something.
Yeah.
So I guess there is the possibility that the contract could move into a situation where every call ends up being valid or reverts, which would be a denial of service. If we could move the contract into a state where it can no longer do anything, that would be a denial of service.
Yes.
So the successful calls approach is somehow, not too concerned with that kind of outcome. Is that fair?
Yes. Well, I think it would be possible to still. So the model is still expressive enough to say that things like the state should eventually reach this some state, and so if you're trying to get to a state eventually of like some success state, the successful calls approach would still allow you to phrase a lemma in the big picture saying we should reach that state. So even if it did get stuck always in a revert state, you wouldn't be able to prove that lemma. I think does that
Yeah, I mean, a successful call would have to happen to move us into the denial of service state.
Yeah.
So, yeah, okay.
Yeah, and you would be able to tell that you were in a denial of service state, like if you could write a lemma like for all inputs, the result is like essentially a reverse, then you would know that you're in that state.
Yeah.
Could you please, very nice talk. Could you please switch back to the slide 7?
That's 7.
Okay, so it seems like your encoding of actions is specific to this contract, but when you were saying that this is encoding of the blockchain actions. So I'm curious, if you want to verify an interaction between two contracts, you would have to define a combined type for action, or that's a pretty big question. Is it correct?
Yes. Yeah. So the idea here, this is currently written by hand, but DeepSEA does include a lot of machinery for generating code, like code automatically. So the medium-term goal would be to have this generated automatically, even for multiple contracts. DeepSEA does have a system for layering of contracts, and so the idea would be to have that built into this once it's being automatically generated.
So, yeah, question?
I do that.
Sure.
So I was a bit confused when you're sort of doing the proof that you're doing, and you've got the step transition.
Yeah.
What level are you actually working at here? Like, are we working at the source level, or are we working at the bytecode level, or somewhere in between? Like, how are you encoding what each of the functions actually does?
Right. So there's a what DeepSEA does is it generates a definition. So it takes the code that looks like this, and it generates a version in Coq, and that version has a refinement proof down to the bytecode.
Yeah.
And so that version, what it looks like, I don't have a slide, but it looks like kind of a monadic style thing that looks a bit like this, just very broadly. Like it'll have like an if, and then I'll have a bit more. It looks a lot more verbose, but it's still readable as like a high level monadic. So it's like a monadic style representation of the function. Yeah. Does that help?
Right. So you're actually making a proof on a function in Coq that's written in Coq.
Yeah.
That is somehow at a reasonably high level, not dissimilar to the original contract.
Exactly. Yes.
Okay.
Yeah. Yeah.
Okay, thanks so much. Okay.
Oh, thank you.